This week we're going to delve into cosmology, starting with an examination of Olber's paradox and Hubble's law. So cosmology is the part of astrophysics which deals with the universe as a whole. It takes the laws of physics and applies them to try to model the whole universe as a single entity, and takes astronomical observations to see if the predictions of our physical model of the universe matches what we see. Cosmological observations is tied up in what is known as Olber's paradox. And Olber's paradox just asks, why is the night sky dark? A seemingly simple question which has far-reaching implications. Let me use an analogy to start with. If you're in a small forest, a small wood, then it's possible that in certain directions you'll be able to find a line of sight that lets you see outside of the forest, so no trees lie in your line of sight. If the forest is large enough, however, no matter what direction you look, your line of sight will end on a tree, and therefore you will not be able to see anything but trees. Well, let's apply the same logic to the night sky. Here we are on Earth looking out at the stars, and the question is, would we expect to see light from stars in every direction that we look in? Well, if the universe were infinite, then every direction you look, your line of sight would end on a star. Right. Now you might say, well, stars get dimmer the further away they are. That's true, but there are more of them the further away you are. In fact, if stars are uniformly distributed throughout the universe, the further away you are, the number of stars that you'll see increases as the distance squared, whereas the brightness decreases as the distance squared. So the fact that the stars get dimmer is exactly cancelled out by the fact that there are more stars. So the conclusion is that if the universe is infinite, the night sky would be blindingly bright. Right? Every single patch of sky would end on the line of sight to every single patch of the sky would end on a star. So why is the night sky dark? Well, there are several ways out of this. The first possible solution is that the universe isn't infinite, it has an edge, or so it is finite. Or alternatively, the universe is infinite, but the actual stars and galaxies run out at some distance from us, and then there's just empty space beyond that. The third alternative is that the universe has a beginning, because the further away we look, the further back in time we're looking because of the finite travel time of light. And so if the universe has a beginning, then we're only going to see as far back as that beginning. Now, the universe might be brighter earlier on, but as we'll see, if the universe is expanding, then light will be redshifted or cooled by the expansion of the universe, and therefore move from visible light to much longer wavelengths. So, as we'll see, the fact that the universe has a beginning is what appears to be the true case. And the first evidence for this came when Edwin Hubble in the 1920s discovered the law that bears his name. These are a series of spectra of entire galaxies. Okay, if galaxies are quite distant, then we don't see their individual stars, we see all of their starlight merged together. So a lot of the variety of spectral lines will be washed out since we're averaging over billions and billions of stars. But hydrogen gas in the galaxies emits strongly at certain specific wavelengths, like the Balmer series, and this is the hydrogen alpha line of the Balmer series. These series of galaxies are further and further away from us, and what Hubble discovered is that the emission line from hydrogen in these galaxies, the further away the galaxy is, the more redshifted that line is. And if it's redshifted, that means the galaxy is moving away from us. So this tells us that the further away the galaxy is from us, the faster it's moving away from us. And outside of our local group, Hubble found that all galaxies were moving away from us. So Hubble's law is that galaxies are moving away from us, and the speed that they're moving away from us is proportional to their distance. In other words, the speed v that they're moving away from us is equal to a constant h times their distance d. H is called Hubble's constant. Now, the speed at which they're moving away from us is measured in kilometers per second, whereas the distance is usually measured in megaparsecs, since we're dealing now with cosmological distances. Those are distances that are a substantial proportion of the size of the universe. Therefore, Hubble's constant has units of kilometers per second per megaparsec. The current best estimate is that Hubble's constant is 67 kilometers per second per megaparsec, and we will explore how we come to this figure next week. It's important to note one thing about this. So all galaxies appear to be moving away from us. That does not mean that we are at the center of the universe. If we teleport ourselves to any other galaxy in the universe, we would observe exactly the same thing. All galaxies on cosmological scales are moving away from each other. There are a couple of common visualizations to try and convey this. The first analogy is the balloon analogy. So if you imagine a balloon that is slightly inflated, and you imagine drawing pictures of galaxies over the balloon, and say we pick two galaxies here, 1 centimeter away and 2 centimeters away from this third galaxy, then we inflate the balloon. Now these galaxies are 4 and 2 centimeters away, so their distance has doubled. But if you are on this balloon here, the distance between this galaxy and this galaxy is doubled, and the distance between this galaxy and all the other galaxies has doubled as well. All of the galaxies have moved away from each other on the surface of this balloon. We saw last week that general relativity predicts that space-time itself, four-dimensional space-time, is curved like the surface of a balloon. And it is space-time itself that is expanding and carrying galaxies along with it. Now notice that when you inflate the balloon, the galaxies themselves are not moving around on the surface of the balloon. It is the fabric of the balloon itself that is expanding, and that is what's happening in the universe. Space-time itself is expanding. The galaxies are not actually moving through space. Another picture is the raisin cake analogy. So if you're making a loaf full of raisins, put it in the oven, you bake it, it expands, the raisins all move away from each other. Okay, if you sit on any raisin, you'll see every other raisin move away from you. The raisins are not moving around inside the loaf, but the loaf itself is expanding and carrying the raisins from them. So this observation leads us to conclude that the universe is expanding. Well, if we run time backwards, that implies that at some point in the past, all of the galaxies were on top of each other. If you carry the sequence back in time to its logical conclusion, all of matter was squashed into an infinitely dense, whose temperature was infinitely high. If you run time forward, then essentially you have an explosion of matter, the universe expanding, and that matter cooling down and condensing out to form stars and galaxies that continue moving apart as space expands. Now we can use the rate at which the universe is expanding today to estimate how far back in time you'd have to go to get to this singularity. And you would find that you have to go about 13.7 billion years back in time. So that gives us our best estimate of the age of the universe. Now, the Hubble law gives us another rung on our cosmic distance ladder, one that is valid to the ends of the universe. This allows us to measure the distances of the most distant objects we can see, or at least the most distant galaxies we can see. All we have to do is measure the redshift of the galaxy. That gives us the velocity it's moving away from us, and then the distance we get from Hubble's law.